Hey guys, how's it going? I just got a supplementary video here. It's actually to do with calculating the appropriate intake runner length uh, for your application. This is something that's just like an FYI. I was curious. I thought it was quite interesting. Stan actually asked me about it, I believe, in one of the classes. Well, sir, what is the ideal length? But the thing is, the ideal length, the ideal would be depending on your application. So I hope this answers your question a little bit. So first, you have to determine what RPM range is your engine in terms of its peak volumetric efficiency based on your cam, based on how it's built. Where do you want that pocket of power to actually occur? So for instance, this is just an example. Let's say 5,000 RPM is where you want the peak power to be appearing on your dyno, right? So first we're going to take that value. We're going to have to figure out how many degrees per second that this engine is going to be rotating. Okay, and how we do that, the first part of this equation is you take your 5,000 revs per minute, you divide it by 60 to determine how many revs per second. Okay, so in this case, it works out to 83.3 revs per second, so revolutions per second. Now to turn this into degrees per second, all I would take is the revs per minute, right? Sorry, revs per second, and multiply it by 360 degrees of crankshaft rotation, and then I end up with 29,988 degrees per second. And the next part of this equation now we have to take into account is the cam specs. And this part of the equation here, this part of the equation, okay, is to do with determining the amount of degrees the intake valve is closed, okay, in the 4-stroke cycle. So in the 4-stroke cycle, the complete 4-stroke cycle, your vehicle, how many degrees the intake valve remains closed. Okay, so first you need your cam specs. This is just a typical cam spec that you can obtain if you want to just shop around, plug in your own values. I just grabbed like a simple single pushrod engine cam spec. So for instance, this cam spec, it's to do with the intake opening duration. Opens 40 degrees BTDC. Okay, so what that means is that's an acronym for before top dead center. And the intake valve closes 80 degrees ABDC, which means after bottom dead center. So what does that mean? So let's just say this is a half circle here. Let's draw another half of the circle. So this is one rotation of the crankshaft. Top dead center technically is 0 degrees up here. Bottom dead center is 180 degrees over here, right? So this cam opens at 40 degrees before top dead center. So let's just do a simulated line here. So this is about 40 degrees. So you would take this and add it to 180. And it's telling you the delayed closing is 80 degrees after bottom dead center, which is here, right? So you take your 80 and then you add the three numbers together to determine the total time. This is the total time your intake valve spends open in the 720 degree 4-stroke cycle, okay? Because it takes 2 full rotations for a 4-stroke cycle to happen, right? So you take 180 plus 80 plus 40, you end up with 300 degrees. So 300 degrees, that's how much time your intake cam spends open in one revolution of the 4-stroke cycle. So how do you determine how long your intake valve, in terms of degrees, how many degrees does it remain closed? So we know that in a 4-stroke cycle, that's basically 360 degrees times 2. You get 720 degrees of crankshaft rotation for every complete cycle, right? You would just take 300 degrees. This is the amount of time this is the amount of degrees. Sorry, I keep saying time. This is the amount of degrees your intake valve remains open. Subtract it from the total degrees of your 4-stroke cycle, you end up remaining with 420 degrees, okay? So 420 degrees, this is the amount of degrees the intake valve is closed. Now, we're going to have to turn this value, okay? You're going to have to find out, okay, we know it's closed for 420 degrees. But in terms of time, in its relationship to time, how long does, the elapsed time of 420 degrees to take place, how much time is that exactly at 5,000 RPM? If you follow what I'm trying to say, you're trying to figure out at 5,000 revs per minute, how much time actually goes by for this 420 degrees to take place. So you would take 420 degrees of inlet valve remaining closed, divided by 29,980 degrees per second, which is what your current engine RPM is, right? Your actual engine speed in relation to degrees per second. You end up with 0.014. So this is actually 0.014 seconds. Okay, and what's the importance of this time? So let's just move on first, and we'll come back to this. The next, we need to figure out what your actual peak your peak airspeed is at this RPM. Okay, now there is a calculation associated with that. Okay, that calculation is basically you got to take your bore area divided by your intake port cross-sectional area multiplied by the mean piston speed. But what's the mean piston speed? Mean piston speed is basically you take 2 multiplied by the stroke of your crankshaft multiplied by your RPM. Okay, so then once you calculate all this together, then you'll get the actual intake port velocity of your engine. Okay, but it's not important what it is in actuality. We just want to prove this equation and show you how you calculate intake runner length. So a typical figure for this type of engine at 5,000 RPM that I had in mind, it's approximately 1,125 feet per second. This is pretty much almost the speed of sound. What we're going to have to do is we've got to figure out basically how many feet does the air travel in 0.014 seconds. We know how fast the air is moving. Okay, this is the rate of speed that the air is moving into that intake port, right up to the intake valve, right? But it only has 0.014 seconds to bounce off the intake valve and go back and forth before the intake valve opens again. So that's a really, really short fraction of a second, okay? So what we got to do is we got to take this 1,125 feet per second, okay, multiplied by the amount of time that the intake valve is actually closed in your engine, which is 0.014 seconds, you end up with 15.75 feet, okay? Seconds units cancel out. So that means when that air charge goes into your intake port, it's going to bounce back and forth. And, I mentioned to you like the tennis ball effect. As the tennis ball bounces back and forth between these two walls, right? It's going to bounce back and forth until the energy dissipates. And if you were to measure if you measure, let's say from here to here, this x is the distance, right? You would go back and forth and add up x, and it's going to add up to 15.75 feet. You understand? So, moving on to the next section, okay? You're going to divide this number by the intake runner length that you have, okay? If it ends up being an odd number, there's two things you got to think about. If it ends up being an odd number, that means the pulse will be conflicting with your combination, right? So remember I mentioned like when you have the intake port here and here's your valve, right? Here's your valve. If it's an odd number, so this is you're the intake valve. You're going to throw the ball out now. You want the ball to hit the wall and then come back at you, yes? Right? So that means it's an even number. If you end up dividing your velocity, okay, if you're dividing your air velocity with your actual runner length, and if the number's an odd number, that means it's the same thing as saying you're going to throw the ball, it's going to bounce back, and it's going to bounce back out. So that's going to conflict with the air coming in to the intake port. So now your next question is probably going to say, well, how do we figure out what the runner length is? First of all, okay, how do we measure? We're not measuring from the cylinder head to the end of the intake, to the end of your actual inlet runner. You have to measure from the back of the valve. So you actually measure from the back of the intake valve all the way out to where your fresh air would be entering on your inlet. It's a total. That's a total length, right? So just for argument's sake, you have a 10-inch runner. All right. So let's see what happens. You're gonna take a 10.5-inch runner. You're gonna take your 15.75 feet. We're going to convert it to inches because we're dealing with inches here, right? It's just an easier unit to deal with. So to convert that to inches, you just take 15.75 feet. We know that there's 12 inches in 1 foot. Just multiply 15.75 by 12. You end up having 189 inches. And again, this figure represents the calculated distance the air pulse will need to travel back and forth in that port before dissipating, okay? But it only has 0.014 seconds to do this. So, back to what I was saying over here. You take 189 inches, you divide it by 10.5 inches, which is, let's say you bought an intake that the runner is 10.5 inches. Your result is 18. Sure, that is an even number. Okay, that is an even number, which is good. But that's this number here, 18 means it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth, back and forth multiple times before it gets to 18. Why is that bad? Why is having too many bumps, like too many deflections, a bad thing? Just remember, here's two walls, yes? You're going to throw the tennis ball. It's going to go over here. It's going to bounce. It's going to go back, and it's going to bounce. And every time it bounces, it's going to get weaker and weaker and weaker. You understand what I'm saying? That each time it bounces, it loses the force that initially was thrown into the ball. Same thing happens with the air. So the whole point of this is we're using this air to help supercharge the next batch of air coming in the engine, right? So wouldn't you want technically you would want the air to go out and then instantly as it's bouncing back, while the force of air coming back is still at near the original amount, so it's still a greater amount of force. The less bumps you have, then you're going to have a greater amount of force pushing the air in. Then your acoustic supercharging effect will be greater, right? So typically you would say, you want the numbers low as possible, but what happens if you make it extremely low, you're gonna end up with a figure where, whoa, wow, I need a 30-inch runner. It doesn't make any sense. That's right? But that's why you have people who cut the hood of their car and they put a tunnel ram, and you have really like a high-rise intake popping out of the hood. That's the same kind of thing. So let's just say I want my figure to be approximately 8 pulses. Let's say I want it to go back and forth 8 times before my inlet valve opens. You take 189 inches divided by 8 pulses, and you end up with 23.6 inch. So let's say if I wanted to achieve 8 pulses back and forth, I would need to put a 23.6 inch runner. Now your question might be, well, what if I want to reduce this lower? This figure is going to get higher, obviously, right? So then to determine where your trade-off is, you'd have to look at, well, how much space is actually under the hood of your car, obviously, right? And also, the application, obviously, manufacturers who are designing a road car, the intake has to fit within the engine compartment. So they would always obviously try to find a trade-off. And this number can be optimized through aftermarket upgrading and whatnot, obviously, right? But I hope this sort of clears it up. I hope this sort of answers your question on how to determine the correct runner length.